Hello everyone, thank you very much for joining my presentation. My paper title is Remodularization Analysis for Microservice Discovery using Syntactic and Semantic Clustering. My name is Anuruddha Alves and my co-authors are Alistair Barros, Colin Fitch and Artem Poliani. I am from Queensland University of Technology in Australia. This is the overview of my presentation. As we all know, in our day-to-day life, we use different software systems to make our life easy. One such software systems we used in enterprises are called enterprise systems. These are used to manage complex business activities related to enterprises. Given the structure of these enterprise systems, different architectural configurations has been used and to create them and evolve the software systems used in enterprises. The first architecture used is called multi-tier architecture, in which they have separated the presentation tier, business logic tier and database tier into different layers. Later on, in order to provide better management of those different tiers and to provide better coding and development and operation advantages, the component-based computing came into the industry, in which they have separated the major functionality related to the software components or software system and developed them as separate software components. However, still the underlying structure was really complex and these software components were really difficult to manage, and the scalability and availability issues were still prevailing in these software systems. The cloud computing was introduced in this particular time to the industry. As such, the service-oriented architecture was developed, in which they try to provide the underlying functionality of a given software system to the third-party users through API calls as services. Given the underlying structure of this software system still stays the same, the system structure was really complex and difficult to manage, and the development and operation time was really high. As such, later on, the microservice architecture was introduced to the industry. Microservices can be defined as highly cohesive software components which are focused to provide a specific functionality to the users. As such, they are highly cohesive components given that they focused on a specific functionality, and they are loosely coupled because their dependency for the other components or other microservices are really low. As such, they are really loose coupled components. On the other hand, because they are focused on a particular functionality and their implementation size, so the code structure is really low, their resource usage is also becoming really low. As such, the scalability becomes really high, and also the availability of and the execution efficiency of the overall system becomes really high. Due to these different advantages, the organizations such as Netflix, Salesforce, Amazon and also Google Cloud try to move their existing systems into cloud as microservices. In order to support these different configurations, you should have a better understanding of the existing system and also the system which is going to be developed using these particular systems as microservices. When we focus on the enterprise systems can be defined as a collection of different software modules which contains classes that have operations manipulating data related to business objects reside inside the database layer. In this situation, we can see a particular software module in the enterprise system can have multiple classes which are related to multiple business objects residing in the database. Also, the operations, those classes can have different class object reference relationship among themselves, and also they can have class subtype relationship amongst themselves. On the other hand, if you think about the microservice system, you can see that there are, in this situation, we focus on a particular business object and operations related to that particular business object clustered together as classes and develop them as a separate microservice reside inside a particular microservice container. Now, in order to develop these kind of systems, different system reengineering techniques were developed to support the developers and to make the execution or the reengineering process more efficient. Mainly, we can categorize these reengineering techniques into two categories, namely named as dynamic system analysis and static system analysis. The static system analysis mainly focus on the code structure of the given system and try to identify the components which can be extracted together as, or classes which can be extracted together as a single component. On the other hand, the dynamic system analysis try to identify the semantics or execution patterns, user behavior related to a particular system. The static analysis can be mainly categorized into two categories, names and structural relationship analysis and conceptual relationship analysis. The structural relationship analysis mainly focus on the class level and method level calls between different classes and methods, and based on those relationships they try to evaluate the coupling between different classes and try to cluster those classes together to create a particular software component. In the conceptual relationship analysis, what they do is they evaluate the conceptual similarity between different classes by using information retrieval techniques. In this situation, they use information retrieval techniques to extract the information related to those classes, and then they evaluate the similarity of the concepts between those different classes and try to cluster them together to create a particular software component. In the semantic relationship analysis, they evaluate the semantics related to that particular software system using execution logs and business object relationships, and then try to derive the components which can be developed together or extracted together. However, there's limited research conducted on how to utilize semantic and syntactic aspects of software systems to identify and develop microservice discovery and recommendation systems. As such is the focus on this particular paper. In order to mitigate those issues, we came up with our microservice discovery approach, which contains 6 steps. Initially, we try to understand or extract the business objects related to the particular software system. We define business objects as a collection of database tables reside inside the database in enterprise system. As such, in this situation, we evaluate the semantic similarities between those different database tables and we group them together into different business objects. Then we move to the static analysis of the legacy system, in which we try to identify the semantic relationships and the syntactic structure relationship existing between different components and the enterprise system. After extracting those information, we provide those information to the CAiSE clustering algorithm, and each provide clustering recommendations to develop microservices. If we initially focus on the semantic structure relationship analysis, we try to identify the class, SQL, and BO relationship analysis in this situation. For this, we extracted the classes related to a particular software system, and then we evaluate the particular class's relationship to a particular business object in the given enterprise system. In this situation, we can see the class 1 related to business object only once, and to business object 3 3 times, and for business object 4 2 times. Basically, in this situation, it identified that there are multiple operations or 3 operations reside in class 1 related to business object 2, and related to business object 1 there is only one operation. After extracting and summarizing those information into a matrix, then we move to the syntactic structure relationship analysis. In this, first we evaluate the structural class similarity. For this, we use information retrieval technologies, and we extracted all the information related to the classes, and then we calculate the cosine similarity between those classes and developed it as a matrix. Then we try to evaluate the structural inheritance relationships and structural interaction relationship existing between the classes. Basically, this captures the parent-child relationship existing between different classes and object-referent relationship existing between different classes. For this, we use Mondrian scripts, and we generated call graphs similar to this one depicted here. And then we summarized those, we extracted information from those graphs and summarized them inside matrices similar to this one depicted here. After extracting all this information, we provide those feature sets to our K-means clustering algorithm, and it uses Euclidean distance calculation to cluster those nodes into different groups such that they can be provided as recommendations for microservice development. In this clustering algorithm, we initially provide only the clustering class and BO relationship information and class cosine feature sets for the clustering process. Then later on we introduce the clustering subtype information for the clustering process, and finally we introduce all the features information for the clustering process. The reason for doing the research reason for conducting research in this manner is to evaluate the effectiveness of introducing multiple feature set in the clustering process. Based on the recommendations provided by these prototypes, we developed different microservices. We tested this prototype against two enterprise systems. First one is Church CRM, which is an open source church management system, and the second one is the Sugar CRM, which is an open source customer management system. The Church CRM contains about 4,000 source files containing 350 attributes divided between 55 tables, which can be clustered as 11 business objects. And when we move to the Sugar CRM, it contains about 8,000 source files, which contain 600 attributes divided between 101 tables containing 18 different business objects. Based on the clustering suggestions provided, we implemented microservices and hosted them in Amazon Web Services and conducted the experiments. The experiments were conducted in two stages. First, we initially used a lift and shift approach, in which we hosted the existing enterprise system as it is in the Amazon Web Services. For this, we use Amazon EC2 instance, as we have depicted in the left hand side of this image, and we synchronize the data related to those systems in a relational database system implemented in the Amazon Web Services. And then we executed 100 to 200 executions using 4 machines, and we generated the load and we execute the system, and we extracted the CPU usage, total execution time, and performance information related to the enterprise system. Later on, we introduced the microservices suggested by the clustering algorithm, and we hosted them in Amazon Elastic Container Services, and we have separate database managing the information related to those ones, and we synchronize those information related to the microservice database system with the backend enterprise system using Amazon Database Migration Service. Then we executed both these systems as a whole together, such that when you send a request to enterprise system, if it needs information from the microservice system, it sends different parameters to the API request related to a microservice system, and then extract the information from that one and then do the processing. And again, we execute the system similar to the previous one, where we executed the enterprise system using 4 machines while generating 100 to 200 executions simultaneously using those systems. Now we want to evaluate the performance improvement we obtain for the microservices when we compare it against the enterprise system. As such, we use 4 performance measurements in this situation. We measure the scalability related to the system. For this one, we evaluate how much extra resources it requires when you improve or when you increase the load for that particular system, and if you use less amount of resources to provide the same amount of execution efficiency, then it means that your scalability is better. Then we check the efficiency improvement of the system. For this one, we evaluate the time difference between the enterprise system execution time and the microservice execution time. The lack of structural cohesion is configured or measured by evaluating how many classes in a particular software model that does not have relationship between each other, and the structural coupling is calculated by measuring how many classes reside inside a particular microservice that has relationship to the external microservices or external components. Based on these calculations, first we obtain the cosine lack of cosine for the systems. As you can see in this situation, the lack of cosine for the for the Sugar CRM and Church CRM, when we introduce multiple features, has been reduced from 484 to 356 in the Sugar CRM, and from 516 to 504 in Church CRM. And then we calculate the structural coupling of the system. Again, when you compare the values, you can see the lack of the structural coupling values has been reduced from 46.77 to 38, and also 41.88 to 34.4 34.81 for church CRM. As such, there is an improvement in the structural coupling values of the components also. Then we evaluate the scalability values and efficiency values for the systems that we introduce. First, we evaluate the scalability values that we obtain for the enterprise systems. As you can see in this situation, the scalability value we obtain for the enterprise system is high, which means it's used a lot of resources when you increase the workload for that particular system. But when you see the green colored section where we introduce the microservices which adhere to the suggestions provided by our clustering algorithms, we managed to reduce the scalability value we obtain for here, which means that we use less amount of resources to achieve the same performance. As such, we improve the scalability. And also when you compare the efficiency values, we managed to improve the efficiency values also for the both systems. In order to check that our algorithm provide better clustering suggestions, we develop microservices which do not adhere to the suggestions provided by the clustering algorithm. And again, we calculated the scalability and availability values. And you can see when you introduce microservices in that manner as depicted in here in red color, the scalability values and efficiency values reduce. As such, we managed to improve the performance and derivation of microservices using the prototype and the suggestions that we provided using our algorithms. When we think about the overall structure of the enterprise systems and the complexity of the enterprise system, it is important to identify the components which can be developed as microservices, and there are limited research conducted on combining semantic and syntactic analysis for discovery of microservices using for those particular systems. As such, in this particular paper, we develop algorithms to derive business object relationships and derive class level relationships using syntactic and semantic analysis, and then derive microserviceable components based on that. It would be interesting to see how we can explore the effectiveness of combining multiple aspects of semantic analysis with syntactic analysis to discover microservices in the future. Basically, in this paper, we only consider about the BO relationship as the semantic analysis, but if we can evaluate the execution efficiencies, amount of data transfer, frequencies, as in the semantic aspects, then it might improve the overall clustering suggestions provided by this prototype in the future. So these are the references I use in this presentation, and thank you very much for your for listening to this presentation and watching it online. Thank you very much.